Hello, in this section, 10.3, we're going to take a break from looking at differential equations for a minute and talk about a concept of Fourier series, which is going to be, we saw a little bit last time, talking about how important it would be to express a function as a series of trig functions. And so Fourier series is the tool that we're going to use to do that, and we want to define it fairly rigorously, so we're going to spend some time talking about how to do that. Now, in this first video, I'm just going to talk about some important concepts of different properties of functions, just kind of as a reminder, and do some groundwork computations that we'll use in the next videos. So first, let's just list some important properties of functions. So a function f of x is, our first one will be piecewise continuous. And that means that, see, on an interval a to b, if it's continuous everywhere except for maybe just a few points. So it can have some discontinuities, but only at certain points, so at finitely many points. And at those points, if it's only going to be discontinuous at a single point, then that means that it has a jump discontinuity. So where it has a jump discontinuity. So let's draw an example of that. We have some axis from A to B, so we're only looking in there, and our function is nice and smooth until it hits a certain point, and then maybe it jumps, and then it's smooth again, or at least continuous, and then it jumps again. And then what's happening at that particular point, it could be, sort of all over the place. Doesn't really matter. So that's what piecewise continuous means, is that you can at least find pieces where it's going to be continuous. And the reason that this concept matters is that even if you break things apart here, you can still take an integral of this function, because these single points don't really matter when you're just adding up the area. So this is still usually integrable, because if you're adding up the area under the curve, you can just sort of break it up there, and those individual points don't matter. All right, so next we say that f of x is periodic of period t if f of x plus t equals f of x for all x in the domain. And then the smallest value of t is the fundamental period. So the classic example of periodic functions are sine and cosine, and they have period 2 pi. And so let's draw that. Let's see. I'm going to draw a couple of examples here. Draw a few different axes. So let's start with sine. It goes like that over to pi, and then over there to 2 pi. So this is sine of x. And so you could say that sine of x has period 6 pi, because that, if you put 6 pi into this relationship here, it holds. But the smallest one, the smallest value of t that you could put in there would be 2 pi, and that's what makes it the fundamental period. And then we have cosine pi, kind of goes like this, over to pi, and oops, there we go, fix that, negative pi to pi. And then another example of a periodic function would be tangent. Now, tangent has these asymptotes at pi over 2 and negative pi over 2. And then kind of goes like this. So tangent of x, oops. There we go. So sine of x has period 2 pi, cosine does 2, and then tangent of x has period just pi. All right, so next we're going to talk about some symmetry properties, and you've probably seen this before. I'm sure we've talked about it in class. So we say that f is even if it's symmetric about the y-axis, which means that f of negative x, if you plug in something on the left-hand side of the graph, then it's just the same thing as if you plug in the value on the right-hand side. So that's for all x in the domain. And then similarly, it's odd if, the way to think about this geometrically is rotational symmetry about the origin. So it's odd if when you plug in a negative value, it is the negative of what you, if you plugged in the positive value. So that's for all x in the domain. Now let's give ourselves some space and we'll talk about some examples. So some examples of even functions. The reason that they're called even, I guess, is that any even power of x is an odd function. So all of these. And then also cosine of x is the other sort of classic example of that. And if you sort of graph this, let's graph it. We'll do it real small like. Cosine of x looks like this. So you can see that that's symmetric around the y-axis. And if you plug in a negative x, you get the same thing that you get on the other side. And then same thing for any of our even powers of x. Those are all going to look like parabolas, basically. So the same thing. Some examples of odd functions are similar. So any odd powers of x, x cubed, x to the fifth, etc. And then also sine of x, and for that matter, tangent of x are odd. And I always found odd a little bit harder to visualize. So let's draw an axis here. And let's start with sine of x. That looks like this. And so you can imagine if you, I guess we can do it right here, if you took this whole thing and ignoring the fact that I drew it really wobbly like, you can rotate this and it'll end up looking like the same thing. So that's what sort of this symmetric about the origin means, if you've ever heard that term before. And then the other way you can see it using the definition is that if you plug in if you've got an x and you've got negative x down here, here's f of x, and if you plug in the same thing over on the left-hand side, you get the same value except down in the negative sign. So that's f of negative x there. And so the other examples would be if you have a x cubed and tangent of x kind of look the same, where they, x cubed sort of goes down on the left-hand side and up on the right-hand side. Tangent does something similar. And so that's where that oddness comes from. Now, even and odd functions have some other really nice properties, especially when it comes to integrals. So we're going to talk about that right now. Let's see, let's call this a theorem. And we've got two parts here. Well, let's see. If f is even and piecewise continuous on an interval that's sort of the same length on either side of the origin, then if we take the integral from negative a to a of f of x, this equals 2 times the integral if you just integrate on the right-hand side. So the integral from 0 to a of f of x dx. And I'm going to do a proof by picture before we go on to the next step. So let's say proof. Got our axis and we've got our a and negative a. And now let's draw our even function. So it's doing whatever it's doing on the right-hand side, and then it's doing the same thing over on the left-hand side. Pretend that that's actually symmetric. And we want to integrate it from negative a to a. And so we could say that we know that this area under the curve here is equal to the integral from 0 to a of f of x dx. And then on the left-hand side, this integral is the same thing. So let's see, this is the same thing from 0 to a f of x dx. And so you can see that the whole integral under the curve from negative a to a is just going to equal the green part plus the red part, which is equal to twice the red part. Now our second statement is going to be about odd functions. So if f is odd and piecewise continuous, that's what PC means, piecewise continuous on negative a to a, then our integral from negative a to a of f of x is going to equal, well, we'll do our proof before we come up with the statement. Hopefully you can see it already. So we've got something that looks like that on the right-hand side, and then on the left-hand side, it's going to have to be the same thing, but down underneath. So the part on the left-hand, or on the right-hand side, is our integral from 0 to a. And over here, we have the same thing, except now it's the signed area, and because it's below the x-axis, it's going to be negative. So the green stuff is actually the opposite, the negative value of the red stuff. And so if you add them together, then it equals 0. So that's going to be a really helpful property for both the sine, or both the even and odd functions when we integrate on this sort of even interval here. So I'm going to stop the video here, and in the next video, we're going to do an example. We're going to evaluate some integrals and really use these properties, and those integrals are going to be important to us as we move forward.